have some practice problems for Charles' law as well. 10 liters of oxygen gas initially at 298 Kelvin is compressed to 5 liters. What is the new temperature? 10 liters is my initial volume. Again, liters indicates volume. Kelvin is my initial temperature. 5 liters is my V2. My new temperature is T2. So if I go back to my relationship, V1 over T1 equals V2 over T2. I'm trying to solve for T2. I rearrange my equation, and I get V2 over T1 times V2 times T1 over V1. My V2 is 5 liters. My initial temperature is 298 Kelvin. And my final volume is 10 liters. What units can I cancel on this one? That's right, I can cancel my liters. This divided by that will give me 149 Kelvin. And we can double check. Our volume decreased. Our temperature is going to decrease. Our volume actually decreased by 10 divided by 5 is 2, so it decreased by twofold. 298, half 298 is 149. So that actually makes sense. Alright, at 100 degrees Celsius, argon gas is a volume of 500 milliliters. If the temperature is increased to 125 Celsius, what is the new volume? Remember, with gas law problems, you must convert everything into Kelvin. So that's the very first thing I'm going to do. So this is my initial temperature. When I convert to Kelvin, I take my degrees Celsius and I add 273. So I get 373 Kelvin. My T2, I take 125, at 273, and I get 398 Kelvin. My volume, I'm just going to leave in milliliters, so I don't need to change any of that. It doesn't ask me for a specific unit for my volume, so I can leave it alone. So I'm going to take my equation, and what am I solving for? I'm solving for V2. This was my V1. Okay, so I'm going to take my equation, rearrange it to solve for V2. V1, T2, divided by T1. So all we do is we plug and chug. So 500 milliliters times 398 Kelvin, T2, divided by T1, which was 373 Kelvin. My Kelvin units will cancel. And my final answer is 534 milliliters. Which again also makes sense because the temperature increased, so our volume is going to increase as well. Our final law is the Gay-Lussac's law. And Gay-Lussac discovered the relationship between pressure and temperature. So he saw that at constant volume, pressure divided by the temperature will give us a constant. Again, this also defines a direct relationship. So as one goes up, the other goes up. Or as one goes down, the other goes down. And gives us the equation P1 over T1 equals P2 over T2. Or again, I can completely rearrange it. P1 times T2 equals P2 times T1. And again, P1 is our initial pressure. T1 is our initial volume, our temperature. P2 is our final pressure. And T2 is our final temp. Alright, so pressure-temperature relationship, as the temperature increases, we're taking a shorter arrow, which means they don't have very much kinetic energy. And if we increase it by adding some heat to the situation, these arrows elongate, meaning that they're moving at a faster rate. So the temperature is increasing. Therefore, the pressure on the canister is increasing as well because the particles are moving faster. Here's a graph of what our pressure versus temperature would look like. It would actually be the same if we had volume versus temperature as well. So practice problems to go along with Gay-Lussac's law. The neon gas at 300 Kelvin has a pressure of 2 atmospheres. The temperature is increased to 400 Kelvin. What is the new pressure? 300 Kelvin is my T1, and we're already in Kelvin, so no converting necessary. Initial pressure, final temp, I'm solving for P2. Take my equation, rearrange it. So P2 is P1, T2 divided by T1. So that's for my problem, get my numbers. 2 atmospheres times 400 Kelvin divided by 300 Kelvin. My Kelvin units are going to cancel. And my answer will be 2.7 atmospheres. Double check our work. Temperature increased, pressure increased. So we did it correctly. Number 2 says that a gas at 300 degrees Celsius has a pressure of 1,000 millimeters of mercury. If the pressure is decreased to 700 millimeters of mercury, what is the new temperature? Right off the bat, degrees Celsius is not cool, okay? We have to convert that to Kelvin. Remember, no matter what kind of a problem you're in, you have to put your temperature units in Kelvin. So, if I take my T1, which is this, 300 degrees Celsius plus 273 Kelvin, gives me 573 Kelvin. Okay. My initial pressure is 1,000 millimeters of mercury. My final pressure is 700 millimeters of mercury. They're in the same unit, so I don't need to convert anything. So I'm solving for T2 in this case, so I'm going to rearrange my equation. P2, T1 over P1 is how I'm going to solve my problem. Plug and chug. P2, 700, and then Hg times 573 Kelvin divided by 1,000 millimeters of mercury. Multiplied by, and my final answer would be 431 Kelvin. So to review, let's talk again about the 3 laws quickly. Boyle's law. He said that as pressure increases, volume decreases. So P1 V1 equals P2 V2. Charles' law related volume and temperature. So V1 over T1 equals, P2 over T2. And Gay-Lussac's law, related pressure and temperature. Okay. These are the 3 types of specific 2 variable equations. In our next unit, we're actually going to be taking all 3 of these and combining them into the combined gas.